welcome back. In our last lecture, we discussed on ion beam and specimen or ion matter interaction and signal generation. Today, we will continue with signal generation and also how different contrast forms through the signals. This is what we will discuss today in today's lecture, particularly continuing from signal generation and how different contrasts such as topography, composition, channeling and ion contrast are generated using an electron ion microscope. Last class we have or last lecture we have discussed on SC1, what is SC1 and what is SC2. So, briefly again SC1s are generated from the near the specimen, near the place where incident beam either electron or ion strikes on the specimen, and the signals generated or electrons generated from that place is called SC1. But when that electrons or ions come inside and interact with the specimen and goes outward or outside with a larger angle, those are termed as backscattered electrons or backscattered ion. In case of ion, it is backscattered ion BSI. In case of electron, it is called backscattered electrons. When those electrons comes out of the specimen, by that time they interact and with the specimen, their energy will become less. So, when energy become less of those ion and electrons, they can produce more SC2. These are SC2, these are SC2. These are SC1 and SC2, and in case of electron microscope, the backscattered electron formation is higher as compared to the backscattered ion formation with ion microscopy, because less number of backscattered ion formation occurs in helium ion microscope, less backscattered electrons comes out from the specimen. In particular, the SC2 in scanning electron microscope in SEM is about 2 to 5 times of SC1 in scanning electron microscope. So, when we talk about secondary electron image in scanning electron microscope, mostly there will be SC2. In many times at the bottom of these photographs there will be detector will be SC2 detector or SC2 detection. On the other hand, with a ion microscope, as the yield of backscattered ion is less, because ions will recoil more and they have negligible or less number of such backscattered ions comes out. Therefore, SC2 is less, and this SC2 is one of the main limiting factors of the resolution. We want the signals from the region where our incident electron or ion falls on the specimen, from that region as small as possible. If they are coming away from the specimen, they are degrading the resolution. Moreover, SC2, if we take the ratio of SC2 and SC1, SC2 to SC1 ratio is certainly much higher in scanning electron microscope, 2 to 5, as compared to the helium ion microscope. Again, SC2 to SC1 ratio depends on the specimen and also ion energy. Incident energy, if incident energy is more, then more backscattered electrons and more backscattered ions also come out. Not only that, materials, as we know, backscattered electrons are used for composition distribution or distribution, because as we increase the atomic number of the material, then more backscattered electrons comes out, and from that brightness difference we can tell some region has higher atomic number material and some other region where lower atomic number elements. That is also we have studied in scanning electron microscope. The same thing here, as we increase the atomic number in the material, the backscattered ion or backscattered electrons also more. So, number of SC2, again number of SC2 per unit path of BSI backscattered ion is less than SC1 per unit path is less than SC1 per unit path of primary ions. So, this SC2 versus SE1 is less for helium ion microscope, but more in scanning electron microscope. This is the one of the main reason again for higher resolution, surface resolution in helium ion microscope. Again, when energy of the primary ion increases, backscattered ion increases also increases. That is common, that is same for electron cases also. And there is another electrons, Se electrons, that is Se3 electrons, that we have also discussed in a scanning electron microscope. So, briefly I will talk about. Once the backscattered electrons come out of this specimen, they can, backscattered electron or backscattered ions comes out of this specimen, they can go and strike the pole piece or objective lens, and once they strike the pole piece or objective lens, or maybe in the wall of the chamber, when they strike in the wall of the chamber, they will also produce secondary electrons, and those are termed as Se3. Because again, why we term it as Se? Because their energy is again less than 50 electron volt, therefore Se3 term. And we can differentiate Se1 contribution, Se2, we can differentiate Se3 contribution from Se2 and Se1 by putting a grid around the sample. So, if we put a grid around the sample and apply a negative potential of let us say whatever, let us say 50 electron volt, then all the electrons emerging with energy less than 50 electron volts will come back, because it is a negative potential. But ions, backscattered ions have a much higher energy, much higher than 50 eV. So, they will come out. Once they come out, strike on the wall or the pole piece, they will produce Se3, and we can know how much percentage of Se3 in our how much percentage of Se3 coming from the sample. And there are approximately 10% of Se3 signal in helium ion microscope for most of the material, many of the material. And this is one thing. Second thing is that the yield of the backscattered electrons, is in the range of 0.5 to 0.1 to 0.5 with the change of atomic number. As the atomic number increases, backscattered electrons yield also increases, but it is in the range of 0.1 to 0.5. But other hand, the yield of backscattered ions significantly vary with the atomic number in the range of 0.01 to 0.02. If we take a ratio of 0.5 to this range, ratio of this to this will be much smaller compared to here. It is varying quite a wide range, and this has a strong consequence on the Se3 image. So, as this is quite widely vary, we can use Se3 electrons, we can use Se3 electrons for imaging purpose to also tell there is a difference of atomic number in my specimen, how the distribution of higher atomic number material and lower atomic number material presents in my specimen. Moreover, backscattered ion yield in crystalline material is strongly affected by channeling than that for electrons. So, as we have studied EBSD, electron backscattered diffraction pattern, and similarly the channeling contrast can also be obtained using backscattered ions, as that we get in case of scanning electron microscope. If we look at this photographs, that what we see here, backscattered ion versus Se3 versus secondary electron image of a polished molybdenum metal. The A1 is the signal from backscattered ion detector, whatever the backscattered ion detector, and the B1 is with 50 volt retarding potential, 50 volt retarding potential, 50 eV. That means, if we are when that is grid, we are putting around the sample, when that is 50 electron volt, then we will collect the image from we will get the image with only Se3 electrons. So, those are coming Se3 electrons comes from the backscattered ions. As you see the contrast difference, they are almost same, quite same, but it is little better. Se3 one is better, the contrast difference is better. So, they give similar, but on the other hand, if without any retarding potential, if we take this is the secondary electrons image, which is contribution of both all Se1, Se2 and Se3, we do not see any clear contrast difference. So, the dark and brightness contrast on BSI and SE3 image, these first two images of a polished molybdenum surface is due to the effect of ion channeling on the grains of different crystal orientation. So, that gives the contrast difference, and therefore, the emerge that means the formation of the backscattered ions and SE3 in the specimen, clear cut difference. That is the advantage of considering SE3 electrons in the imaging purpose or backscattered ions for the imaging purpose. Again, another important things this was about the signal detection SE1, SE2, SE3, how they contribute to the imaging purpose. If we look at the ion as incident beam, ions have a significant mass, therefore, it can do a certain damage to the specimen. We cannot completely neglect, though in helium would do less damage or almost negligible damage if we do not use very high energy helium ions, but still it can have a effect. Due to very small wavelength of helium and very focused probe, helium ion microscope provides good resolution and also large depth of field that we have discussed before. It can potentially cause the damage in the sample at the surface because of its large mass. Because of its large mass. So, it is important therefore to control the dodge of ions when it falls on the specimen. For example, the ion dodge can be written as like that can be, we can say, aerial dodge. Aerial dodge can be presented with a symbol, let us say sigma, which is nothing but number of ions per centimeter square. And if we talk about aerial dodge rate is applicable when for example, it causes some consequence, let us say ion dodge forming some thermal effects or charging effect to the specimen, and then the thermal effects or the temperature will dissipate with time as a function of time. Similarly, charge will dissipate with function of time, then in that cases we can write as a per second, ions per centimeter square per second. If we talk about the rate of aerial dodge to compare with how the thermal effects happening in the sample. Okay, this is about damage. We do not want damage in the sample for microscopy purpose. So, we want to have the dodge as less as possible. As long as it can provide us enough signal. If we take too much low dodge, then it would not provide such signal, enough signal that we cannot utilize for our imaging purpose. We should use an ion dodge which should be good enough to produce enough signal. So, we can say that previously we discussed about SN by N S by N signal to noise ratio we have discussed before, or SNR, I can say signal to noise ratio, SNR, signal to noise ratio. Let us say our incident number of incident ions, let us say Ni is our number of incident ions, and we want to detect the signal. Detect means detect the signal means detect the particle, let secondary electron or backscattered ions. So, those are called signal. So, let us say Nd is number of detected particle. So, the yield then therefore yield will be y will be equal to Ni by Nd, sorry, it will be Nd by Ni, number of detected signal divided by number of incident signal, yield y. So, we can write the signal to noise ratio is nothing but root over of Ni, average number of ions incidenting on this specimen, and which is equal to root over of y plus 1 plus y. This we can write signal to noise ratio, or is it nothing but signal to damage ratio in this case, because we want less damage and more signal. So, signal to damage ratio should be as high as possible. Then we know this signal to noise ratio should be at least 5, 3 to 5 at least to have a better contrast on the image. So, in order to have signal to noise ratio approximately 5, we should have around, let us say Ni should be around 25. 25 number of ions means that the root over of 25 is equal to 5. And then this aerial dodge also depends on the region, the area on which ion beam striking. So, sigma is nothing but is equal to Ni, that is number of ions, divided by field of view, f of v. Field of view, that means that area on which the ions is being incident on this specimen. So, now if we put let us say this equation 1 and equation 2, if we put Ni from equation 1 to equation 2, then this sigma can have S n r to the power square, then f of v b square plus 1 by y. This will be signal, this will be our dodge, ion dodge. Now, this ion dodge sigma should be less than the critical value at which it can start damaging the sample or producing undesirable effect. The sigma aerial dodge should be less than the critical value that it could produce the damage. In some cases, that is not an important. For example, if our material itself is amorphous, now dodge is more, it will again amorphosize the material. So, it is not a problem. Or for example, if we are using a very thin section, thin surface, and then ion beam will go and penetrate deeper into the specimen, and then damage will be created in the soft surface, not at the very surface. So, that then also it is not a problem if we take ion dodge little to be more. But for other cases where we want to see the information of the specimen surface, very surface of the specimen, then this ion dodge should be as less as possible. So, then field of view in order to have a ion dodge less, according to the formula, signal to noise ratio should be good, and yield also supposed to be good. Then we talk about different contrast mechanism. There are several factors that determines the contrast in case of helium ion microscope. Some of those are like topographical contrast. Topography means 3-dimensional formation of the image, more the tilt of the sample, more up and down of the sample, giving the 3D features. This is the topographical constants. Then second is material or composition contrast. Material different is there, some places higher atomic number material, some places low atomic number materials. Then we should about to distinguish them, that is material or composition contrast. Then ion channeling contrast, we have discussed about electron channeling, and this is ion channeling because ion beam is incidenting on the specimen. Then voltage contrast, this we have discussed, this is important for semiconductor industry or chip making industry, where lot of circuit devices are there. If there is a circuit break by applying a potential, and then we can know from where secondary electrons will generate or not, that is a voltage contrast. Magnetic contrast, depending on the magnetic domains, they align, magnetic field will be aligned in different direction, they will facilitate generation of the secondary electrons or not facilitate generation of secondary electrons, and that way we could find the contrast difference, that is magnetic contrast. Optical contrast, depending upon the optical nature or of the material, that can give luminescence, like in previous scanning electron microscopy case we have discussed about cathodoluminescence because electron was bombarding on the specimen, but in these cases we say it is ionoluminescence because ion is bombarding on the specimen. We will not discuss much on the voltage, magnetic and optical contrast because they are almost similar to the scanning electron microscope case, only the performance of the helium ion microscope case is a little better. So, it is almost same as the phenomena and consequences are almost same, but so quality the performance is better. On the other hand, the principle is same. We will only discuss the top 3 and the top discussion on the top 3 is also similar manner as scanning electron microscope, but for the sake of the superiority of helium ion microscope, we will be discussing to familiarize you with about the superiority of the helium ion microscope. We will discuss about the first 3 contrast mechanism. Let us see first topographical contrast. What is the difference here? As you see here, This is a sample is a textured silicon. The first two A and B are the scanning electron microscopic image. One was at a very high acceleration voltage 15 keV and second one is 1 keV. Now, you see the difference in the surface. In the first one you do not see the clarity of the surface, because in this case electron beam is penetrating much deeper into the specimen and the information or signals is generating from not from this very surface of the sample, but rather from a certain depth of the sample. Therefore, you do not see the surface information in the first cases, because here energy of the incident electron is much higher, electrons are penetrating much deeper and the information is coming little deeper of the specimen. So, surface information is not clear in the first cases. Again, in scanning electron microscope, by using a lower energy incident beam of electrons like 1 keV, now electron beam will not penetrate much deeper, it will penetrate less on the surface, less to the sample specimen, and therefore, signals will be generated more close to the surface, therefore, the more surface clarity is there. Third one is our helium ion microscope. As you see, the clarity of the surface is much improved with a helium ion microscope, because here only SE1 is coming, is used more SE1 to SE2 ratio will be much higher in these cases, much higher, therefore, giving not only better resolution, but also better clarity. In addition to that, if you look carefully, this region is not very clear, but you see this region are much clear with helium ion microscope, because it is a larger depth of field. We can use smaller alpha value, that is angle of aperture or angle of divergence angle, half angle. So, now in helium ion microscopy we are again using high acceleration voltage, because otherwise we cannot have enough secondary electron shield, because the mass of the helium is quite large. So, we have to put higher acceleration voltage, so that to have a certain velocity, so that it can penetrate to an extent of the surface. This is the topographical constant, which is much superior with helium ion microscope as compared to the scanning electron microscopy. Material contrast, if you look at the material contrast, as you see here in the left side table, different materials having different atomic number have different yield at 20 keV. You see large difference in the secondary electron yield when ion beam interacts, especially this helium ion interacts on the specimen. And then you see here the helium ion produce typically in the range the signal to the number of secondary electrons. This is number of secondary electrons generated per single helium ion, So, if we see this ISI, then it is almost in the range of 2 to 8, unlike in case of electron it is 1 to 1.5. This value will be 1 to 1.5 with electron beam, one electrons in the beam, and therefore, signal is certainly much higher. So, it could produce much higher signal to noise ratio, giving you much clarity on the surface image, much clarity on the image. In addition to that, if we look at these two photographs in this same place, it is a cross, and what we see in SCM, it is certainly giving 3-dimensional image. It is a very good image, it is quite a good resolution, but you see the contrast difference in this region. Middle part of helium ion microscope is quite dark. Also, it is quite dark here. It indicates that this portion are from different material, which do not produce enough secondary electrons. So, this is what material contrast or composition contrast, that we do not see here. Almost the contrast brightness and the brightness is almost similar, but here a quite distinct difference in the darkness brightness in helium ion microscope. This is due to materials, because the number of secondary electrons generated from this region is much less. This contrast we can only get with helium ion microscope. If we talk about ion channeling contrast, ions channeling means that is electron channeling. In previous cases, ions will channel inside the specimen and then they will come or not come. When ion channel more deeper into the specimen, then less number of secondary electrons will come out. If we do not channel much deeper into the specimen, more secondary electrons will come out, and therefore, it is giving different contrast level. This image is with backscattered ion detector, though secondary electron ion detector also gives similar photographs, and contrast level for ions is 8 to 10 times higher than with electrons. Moreover, no channeling pattern is formed with helium ion microscope. In our scanning electron microscope, there is channeling pattern formed. There is a lines of pattern formed. Here we do not form this, because here the wavelength is much smaller compared to the electrons. As wavelength is much smaller in these cases, no channeling pattern is formed, but channeling contrast is very good, and this channeling contrast is very important when you have a thin film, in case of, because this is coming from the surface only. If it will be much bulk and much thicker film, then the signal will become less, in this case helium ion microscope. In case of scanning electron microscope, we want bulk sample, so that because that happens with backscattered electrons, the channeling comes from the backscattered electrons. So, because backscattered electrons come little deeper of the sample, therefore, having a bulk sample, thicker sample is one of the requirement for scanning electron microscope, but it is not here. Here we would prefer to have a thin film or information from the surface. If we want information from the bulk, this is not suitable, then one should go for scanning electron microscope. This is ion channeling contrast, then backscattered ion imaging. Like backscattered electron imaging, we can also use the backscattered ions, though the yield is less backscattered ions, but that still can be utilized for the purpose of imaging purpose. As I have discussed, I have talked before, the range of the backscattered ions with different atomic number varies much wider range in helium ion microscope or ion microscope as compared to the scanning electron microscope. Here you see the energy, here you see the left side image is a secondary electron image giving the topographical constant, but the right side was a backscattered ion image. Clear same solder place, some solder bump. This is a lead tin solder bump, giving a quite drastic difference in the contrast level. This region is much brighter because it has higher atomic number, lead has higher atomic number compared to the darker region where it is tin, where low atomic number. And when the ions bombard on the specimen, it will transport its energy to the atoms, and then some of its energy will be lost, but still some of the ions will be backscattered, and those ions have energy quite high also. And it depends on what will be the energy of the backscattered ion, depends on the atomic number of the target sample or the specimen. The energy of the backscattered helium ion is determined by the atomic mass of the target nucleus and the angle of the scattering. Higher the atomic number, more energy will be the backscattered ions. So in addition to that, number of backscattered helium ions will be proportional to the Z square or atomic number square. So, as we increase the atomic number, more backscattered electrons will come out, as you see here. That is why it is giving much brighter in the image, and that would tells the difference between which region has higher atomic number material and which region has a lower atomic number material. Then ion dependent contrast. Ions, we have so far talked about helium ion microscope or helium ion, but by changing helium to other ions can also produce a drastic contrast difference. For example, that is what you see here. We go ahead, we stop here for today, and we continue with this ion dependent contrast in our next lecture. But before that, what I would like to tell you that we have discussed about the interaction volume. The interaction volume is much smaller in case of ion microscope as compared to the electron microscope. Moreover, and second thing is the signal generation. Signal will mostly come from the surface, because again ion will not penetrate much deeper. So, it will interact near the surface. So, signal will be coming much from the surface, giving us much higher surface resolution. Again, the ratio of SE1 to SE2 is much higher. SE1 to SE2 is much higher with helium ion microscope, because more SE1 are generated, and SE1s are generated from where the incident beam strikes. because ion beam will not penetrate first, it will not penetrate much, and even though it penetrates to an extent, it will recoil here and there, and that chance of forming a backscatter ions is less. Therefore, it will produce less backscatter ion. As it produces less number of backscatter ions, chances of formation of Se2 is also less. Therefore, Se1 to Se2 ratio is higher, and that gives us the superior resolution, surface resolution with a helium ion microscope. What more we have discussed that the topographical contrast depends on the tilt angle. So, when tilt angle is more, then topography, that means electron, that means secondary electrons coming from helium ions is much higher. So, for example, we have seen before the tilt angle in tilt angle degree, and here the yield SC yield, we have seen that for ISI, ISC with helium ion is much larger than SC with SCM, because yield is much higher with tilt angle. Topographical contrast is again better with a helium ion microscope. This is what also we have discussed today in last couple of classes. So, these are the important points that makes helium ion microscope much superior to scanning electron microscope. So, in our next class we will discuss on the next lecture, we will discuss on more about a little more about contrast, and today we stop here. Thank you.